Section 16.3, Path Independence, Conservative Fields, and Potential Functions. So this is a section that is following up on our previous section on vector line integrals. Vector line integrals are very important for us, and so the point of this section is showing that if your vector field that you're integrating has some special properties to it, then there's a lot of really cool consequences you can get from it. And so, as it turns out, if it's conservative, we'll make sure that we carefully define what it means for our vector field to be conservative. In the section here, it will have path independence property. We'll see all of that later on in these videos. So you need some learning goals here. You need to know appropriate definitions such as conservative, what it means for a vector field to be conservative, what are potential functions for vector fields, path independence. You should also know and be able to apply the fundamental theorem of line integrals. That's something that we'll be seeing later on. You should be able to compute and use potential functions. Okay, so as an example, as a motivating example here, I want us to do this problem here together. And you might not see why I'm doing it. This should just feel like another 16.2 problem. I promise there's a reason for doing this. The payoff will be nice here. So compute line integrals of this vector field. It's just a two-dimensional vector field, x squared times y, comma x cubed over 3. And we're going to integrate from 0, 0 to 1, 1 along two different paths. So this is asking us to actually do two different vector line integrals. So one of them, both of them are going to go from the point 0, 0 to the point 1, 1. But C1 of t, R1 of t, I guess I should say, is going in a straight line. And then C2 of t is following the parabola y is equal to x squared from 0, 0 to 1, 1. So two different problems for us to do. Let's just jump right in. We already have our parametrization here. This is good. Let's see here. We know I need to get rid of that marker. We know we'll be needing R1 prime of t. The derivative here is just 1, 1. We know we need f of R1 of t is going to be plugging x as t and y as t. And we get t squared times t is t cubed over 3. And so f of R1 of t dot R1 prime of t, this dot this will give us t cubed plus t cubed over 3 is 4t cubed over 3. We also need to do the same calculations for R2 of t. So let's go ahead and do that. R2 prime of t. T comma t squared, so the derivative of t is 1. Derivative of t squared is 2t. F of R2 of t. Okay, so this will be x is t, so t squared times y is also t squared. So t squared times t squared is t to the 4th. And we still have t cubed over 3. Okay, so let's see here. We also need f of R2 of t dot R2 prime of t is going to be this dot this will give us t to the 4th plus 2t times t cubed over 3 plus 2/3 t to the 4th. So this is 5/3 t to the 4th. Okay, so our integral over c1 of f dot dr is going to be the integral t runs from 0 to 1 of 4/3 t cubed dt. And this is 1/3 if you crunch it out. The integral over c2 of f dot dr is going to equal the integral over from 0 to 1 of 5/3 t to the 4th dt. And then you crunch this one out, you also get 1/3. And so let's take a moment to appreciate what happened here. The integral from 0 to 1 of c1 was 1/3. Integral along c2 from 0 to 1 along c2 of the same vector field is also 1/3. So what this shows is that it didn't matter whether you took the path c1 or the path c2 to go from 0 to 1, your vector line integral of this vector field is going to be 1/3 in either case. And one big point to make here is that there's something special going on here. So we'll see in the future, this is the motivating example here. We'll see in the future, there's something special about this vector field f. There's some special property here that makes it have this property that these two vector line integrals equal. And in fact, any curve that you could take, this was C1 to C2, if we made this curve C3 that started at 0, 0, end at C1, it doesn't matter how weird it would be, if we compute the vector line integral, we would still get 1/3. And so this is a hint. Let's just go back to the title slide of the section here. Path independence. This is an example of path independence. We'll have to define that carefully later on. And there's something special about this vector field here. The answer is that it's conservative, which is closely related to potential functions. This all motivates it. We'll definitely be coming back to this example later on after we've worked out some machinery.